Hi everyone, I'm Chen. Today I'm going to talk about my thesis project, Minimizing Class Imbalance Problem in Steep Stage Classification with Deep Learning Methodology. Steep stage classification analyzes various stages of steep to evaluate steep quality with physiological signals, especially EEG brainwave. The steep stages include wake, rapid eye movement, and non-rapid eye movement. Rapid eye movement and non-rapid eye movement is also called REM and non-REM. Non-REM is considered as deep sleep, which is further divided into three stages, N1, N2, and N3. Automatic feature extraction-based methods, utilizing deep learning algorithms, can minimize the need for feature engineering, and it can extract features without human bias. For the current mainstream methodologies, N1 stage have low accuracy due to the low volume of data available comparative to the other steep stages. Therefore, the ability to sample and augment the data for N1 stage is a critical part of developing a more accurate analysis system of steep stage classification utilizing a deep learning methodology. The proposed methodology utilizes sampling-based methods, data augmentation, and cost function-based methods in an architecture based on steep EEG nets, including convolutional neural network and a sequence-to-sequence model. A dataset of EEG epochs and corresponding labels is the input to the model. The model inserted the augmented and sampled data to steep EEG-based architecture. Then the predicted stages are output from the model. Systematic sampling methods sampled EEG epochs through the selection of every kth element to improve the efficiency of the training process without sacrificing accuracy. Oversampling and data augmentation methods generate a relatively balanced dataset. I was using three oversampling methods, including random oversampling, synthetic minority oversampling, and adaptive synthetic sampling methods, and four data augmentation methods, including jittering, scaling, time warping, and permutation. Two loss functions are proposed, which are weighted mean square false error and focal loss. The false error is calculating the false positive and false negative rates in the confusion matrix. Then higher weight is assigned to N1 stage to bias the model to focus on the minority class. Focal loss is designed to address class imbalance problem by reshaping cross-entropy loss to downweight inliers. Extensive experiment conducted on steep EDF datasets, considering steep EEG nets as the benchmark model, utilizing systematic sampling by selecting every second element, can achieve performance comparable to the benchmark model with only spending 51.6% of the original training time. And the F1 score for N1 stage is 2.2% higher than the benchmark model. The smart oversampling methods with mean square false error loss function gave the best performance. Data augmentation approaches were able to create a relatively balanced dataset, which could help the model to learn more effectively. Each data augmentation method performed well on augmenting data on different stages. However, data augmentation techniques were not able to be used with a systematic sampling strategy, as systematic sampling brought negative effects to the performance of data augmentation. For the network architecture and model tuning, experiments were conducted with different optimizers, regularization approaches, and a number of layers in the CNN structure. Gradient descent optimizer with 0.05 learning rate achieved the best performance. Dropout and batch normalization had similar regularization performance. The proposed model, with fewer layers in CNNs, had half of the number of trainable parameters compared to the benchmark model, which provided the best performance among all the experiments and outperformed the benchmark model. Please feel free to contact me if you have any questions. Thank you.